Hello and welcome to the Deep Dive. Today we're embarking on a journey into a concept that is, well, both fundamental and exquisitely complex. It's something that subtly shapes everything, from, the intricate patterns on ancient walls to the very structure of the minerals beneath our feet.
It really does.
We're talking about symmetry, but this isn't just about recognizing pretty patterns. We're going deep.
Deep into crystallographic symmetry.
Exactly. Unveiling the hidden architecture that defines the precise, repeating order within matter itself.
It's truly a fascinating subject because, while we intuitively recognize symmetry in countless everyday objects,
Right, we see it everywhere.
understanding its rigorous rules at the atomic level reveals a precision and an order that is, frankly, astonishing.
Yeah.
It underpins how crystals form, why certain materials behave the way they do.
And even how we can design new ones.
Exactly, and even how we can engineer new substances with specific tailored properties. It's like the universe's secret language of structure.
Exactly. Think about it.
Yeah.
You see a perfectly formed salt crystal, right? Or maybe a glimmering gemstone. And you instinctively sense an order there. But what's behind that order? What are the profound mathematical rules governing its existence and its appearance?
That's the core question.
And that's our mission today. We've meticulously sifted through a diverse stack of sources from, dense chemistry and physics textbooks,
Mathematical treatises.
elegant mathematical treatises, rich historical accounts, and the very cutting edge of material science research.
A real mix.
Our aim is to give you the clearest, most structured understanding of this topic, breaking down what might seem like daunting complexity into captivating insights.
Sort of like a shortcut.
This is your shortcut to being genuinely well-informed on a subject that, once you start to grasp its implications, is absolutely captivating.
Our goal is to extract those truly essential nuggets of knowledge. Not just definitions, but the so what behind them.
Yeah, the real meaning.
So you can appreciate the elegant, often surprising mathematical constraints and the hidden order that shapes our world one crystal at a time. It's about seeing the invisible architect at work.
Okay, let's unpack this. Symmetry isn't just for geometry textbooks, is it?
Oh, definitely not.
It's literally everywhere you look. And even in places you might not expect. We see it constantly in the natural world.
Absolutely.
Take, for instance, the intricate arrangement of petals in a flower. You might observe a rose, right? With its nearly perfect radial symmetry,
That rotational symmetry.
often exhibiting an axis of rotation, where if you turn it by a certain angle, it appears identical.
You see flowers with order 8 symmetry, meaning 8 identical petals.
Or even order 5, I read, with like 2 distinct families of petals.
Yes, creating these mesmerizing spiral patterns sometimes. It's beautiful.
Or consider something as delicate as a butterfly. There's that clear plane of symmetry, dividing its body and wings into 2 almost perfectly identical halves.
It's quite remarkable, isn't it? What's fascinating here is how intuitively we humans recognize symmetry.
It signals something, doesn't it?
It signals consistency, balance, and a certain kind of repetition in space or time. But often, the deeper implications of that repetition, the underlying rules governing it, they go unnoticed.
Right.
And beyond purely visual examples, we can find symmetry in abstract ideas too.
Like what?
Think of the predictable, rhythmic succession of night and day. That's a time symmetry.
Ah.
Or the recurring motifs, phrases, and structures within a complex piece of music.
Repetition and variation.
Exactly. It's
Yeah.
all about recognizing patterns and transformations that leave an underlying essence unchanged.
And sometimes symmetry even pops up in language in really playful, almost baffling ways.
Oh, yeah.
I found this amazing example that's just a delight. The phrase, a man, a plan, a canal, Panama.
Ah, the classic palindrome.
Right. If you strip away the punctuation and spaces and just read I'm on a plan, a canal, Panama backward.
It's exactly the same.
Exactly the same. It's a complete reversal that leaves the core unchanged.
That's a truly clever example. It's similar in concept to palindromic numbers like 232 or 679976.
Which read the same forwards and backward.
Precisely. This linguistic quirk playfully introduces the concept of reflection or reversal symmetry, where something reads or appears the same from opposing directions.
It's a perfect, accessible lead-in to understanding how we formally define symmetry in a scientific context.
Which is much more rigorous than a fun phrase, but, equally elegant in its own way.
So, broadly speaking, when we define symmetry, we're talking about a transformation, a movement or an operation that leaves an object's overall appearance unchanged. It's about finding operations that make something look exactly the same before and after the change.
That's the essence of it.
And what's particularly interesting for those who appreciate the history of science
Yeah.
is that the fundamental understanding of crystal morphology and these very symmetry elements we're about to discuss was actually established quite a long time ago,
Way back.
between the 17th and 19th centuries, long before we had the tools to see atoms directly.
It was all about careful observation and mathematical deduction. Really impressive stuff.
Here's where it gets really interesting. When we talk about symmetry, especially in the precise, ordered context of crystals, we're not just talking about a general pleasing aesthetic.
Yeah.
We're referring to specific, measurable operations that transform an object but leave it looking absolutely identical.
That's the crucial part. Identical.
These are the fundamental elements of symmetry, the very building blocks of crystalline order.
You've hit on the core concept. These elements are the fundamental operations that allow us to precisely describe the inherent order within any object.
Whether it's simple or complex.
Doesn't matter. A simple geometric shape, a biological molecule, or the incredibly complex internal structure of a mineral. Each operation has a specific, repeatable effect.
Okay, let's start with the absolute simplest, almost philosophically profound maybe. The element, identity.
The identity operation is precisely what it sounds like.
Yeah.
It does nothing at all.
The do-nothing operation.
Exactly. Every single object, without exception, at a minimum, possesses identity.
Seems trivial.
Well, it seems trivial at first glance, but it's crucial because it's the baseline. It's the starting point from which all other symmetries are measured.
Ah, okay.
If an object has no other symmetry, it still has identity, and that's a key part of defining its symmetry group. It's the self-evident truth of symmetry.
Right, like if you just look at something and then look at it again, nothing's changed.
Yeah.
Obvious, but necessary.
Necessary baseline.
But then we have more active transformative operations
Yeah.
like reflection, which involves what we call a mirror plane.
With reflection, you can visualize placing an object in front of an imaginary mirror plane.
Like looking in a mirror.
Pretty much. The image appears perpendicular to this plane, equidistant from it, but on the opposite side.
Okay.
Now, the absolutely critical distinction here, which has profound implications in chemistry and material science,
Yeah. What's that?
is whether the resulting object is distinguishable or indistinguishable from the original.
Distinguishable or indistinguishable? What's the difference mean practically?
Normally, in a general sense, the reflected image is distinguishable, meaning you can't superimpose the reflected image onto the original by simple rotation and translation.
Like our hands?
Exactly. Think of your two hands. They are mirror images of each other, right?
Right.
But you can't perfectly stack one on top of the other to match all their features. They are enantiomers, which we'll definitely delve into shortly.
Right. Non-superimposable mirror images.
But, and this is important, if the reflection plane passes through the object, dividing it into two identical halves,
Like cutting an apple perfectly down the middle.
sort of, yeah, then the object itself can be considered indistinguishable after this conceptual operation, as it perfectly mirrors itself internally.
Okay, so it depends if the mirror is outside or inside the object's symmetry.
In a manner of speaking, yes.
So it's like our left hand reflecting to become our right hand. They're related, but fundamentally not superimposable. What about inversion? This sounds a bit more abstract.
Inversion works through a single imaginary central point within the object, called the inversion center.
A single point.
Yes, every part of the object is moved along a straight line through this inversion center to an equal distance on the opposite side.
So like flipping everything through the middle point.
Kind of like flipping the object inside out through a single central point, yeah. And again, the same key distinction applies. The resulting object can be distinguishable or indistinguishable from the original.
Okay.
Most often, for an external observer, it's distinguishable if the inversion center isn't an inherent part of the object's internal symmetry, meaning it cannot be superimposed.
But if it is part of the symmetry,
But if the inversion center is inside the object and the object possesses this symmetry, such as the center of a perfectly symmetrical polyhedron, like a cube,
then it looks the same after inversion.
then the object can appear indistinguishable after the operation. Yes.
Then we have rotation, which is probably the one most people think of first when they hear symmetry.
Absolutely. We see rotational symmetry everywhere, from spinning wheels to flower petals.
Right.
And rotation in crystallography has two main types. proper rotation and improper rotation.
Okay, what's proper rotation?
A proper rotation involves rotating an object 360 degrees divided by n degrees around a fixed line, which we call the rotation axis.
And n is the order.
Here, n is the order of the axis. For example, a threefold rotation means turning it 120 degrees, 360 divided by 3, and it looks identical.
Assuming it have threefold symmetry.
Right. The object is always indistinguishable after a proper rotation, assuming it actually possesses that particular rotational symmetry.
An improper rotation. Sounds tricky.
An improper rotation is a bit more complex. It's a composite operation. It's a proper rotation, 360n, followed by a reflection through a plane that is perpendicular to that rotation axis.
So a twist and a reflection.
Exactly. Think of it as a twist and a flip. Similar to reflection and inversion, the resulting object can be distinguishable or indistinguishable.
And it's only indistinguishable if.
It's only truly indistinguishable if the improper rotation axis passes through the object and the object intrinsically possesses that particular symmetry.
This concept of distinguishable versus indistinguishable images seems incredibly important.
It really is.
This raises an important question. If some symmetry operations produce distinguishable images, what does that mean for the objects themselves, and why should we care?
This leads us directly to the crucial concepts of chirality and enantiomers, and these have profound implications across physics, chemistry, and biology.
Chirality, like handedness.
Precisely. Chiral objects are those that, by definition, do not contain any center of symmetry or plane of symmetry. Your left hand is the quintessential example. It is chiral because it cannot be superimposed on its mirror image.
My right hand.
Exactly. When a chiral object is reflected through a center or plane of symmetry, the resulting image is its enantiomer. So the mirror image of your left hand is its enantiomer, which looks exactly like your right hand. They are non-superimposable mirror images.
And this isn't just a fun concept. It has huge real-world implications.
Right.
Particularly in areas like pharmaceuticals, I recall hearing.
Absolutely. The implications are immense. In fields like drug design, agriculture, biochemistry, chiral molecules can have vastly different properties from their enantiomers.
How different?
Well, one form, known as an isomer, might be a beneficial drug that fits perfectly into a receptor in the body.
Like a key in a lock.
Exactly. While its mirror image could be completely inert, or worse, even harmful.
Wow.
A famous historical example is thalidomide. One enantiomer was a sedative, but the other caused severe birth defects.
That's horrifying. So distinguishing them is critical.
Absolutely critical. Accurately determining the absolute configuration or structure of a molecule differentiating between these enantiomers is often done through advanced X-ray diffraction techniques. It's a crucial tool in modern science, ensuring safety and efficacy in countless applications.
That's incredible. So these basic elements, identity, reflection, inversion, proper and improper rotation, are like the fundamental alphabet, the irreducible set of operations for describing how anything, especially matter at its most ordered, is structured.
That's a great way to put it, the alphabet of symmetry.
Okay, so we've talked about symmetry in general, these fundamental operations, but what makes crystals so special in how they display symmetry?
The key difference.
It all comes down to their fundamental defining characteristic. Periodicity.
Yeah.
This isn't just about things looking the same, but looking the same regularly repeating in space.
Precisely. Crystals are not just symmetrical, they are periodically symmetrical, and that's a critical distinction.
Periodically symmetrical.
This means they are defined by the ordered periodic repetition of basic motifs, which can be individual atoms, molecules, or ions, in 3 dimensions.
Like bricks in a wall.
Exactly. Imagine not just a single brick, but an entire perfectly constructed wall where each brick is identical and stacked in a precise repeating pattern throughout its entire length and height.
Okay, I can picture that.
This consistent, predictable, repeating arrangement is what fundamentally distinguishes a crystal from an amorphous solid like glass.
Which is disordered.
Right, and it's what gives crystals their unique and often highly directional properties.
So if you imagine that brick wall, you can intuitively pick out a single brick as the basic repeating unit. In crystallography, we call that the unit cell. It's the smallest representative volume.
Yes, the unit cell is the fundamental concept. It's the smallest block, the irreducible volume, whose simple repetition through translation alone generates the entire crystal lattice.
Translation meaning just shifting it.
Just shifting it in space, yes. It's absolutely crucial because its shape, size, and internal contents characterize the entire crystal's structure.
And how do we describe it?
Well, we describe a unit cell by the lengths of its three edges, typically labeled A, B, and C.
3 dimensions.
Right. And the angles between those edges, alpha, beta, and gamma. These 6 parameters, 3 lengths and 3 angles, completely define the geometry of that tiny repeating box.
And there are different types of unit cells, right? Like primitive and non-primitive. What's the distinction and why does it matter?
That's correct. A primitive cell is the simplest possible unit cell. It contains a total of 1 motif, or lattice point, per cell.
Only one building block inside.
Effectively, yes. If you imagine a 2D grid of points, a primitive cell would be the smallest parallelogram connecting 4 points. Each point at a vertex effectively contributes a fraction, like a quarter in 2D, summing up to 1 complete point inside the cell.
Okay. And non-primitive.
Non-primitive cells, on the other hand, contain more than 1 motif per cell volume. For example, you might have points at the vertices plus a complete one exactly in the center of the cell.
Body-centered.
That's body-centered, yes. Or on the faces of the cell.
Face-centered.
Right. These distinctions matter because while primitive cells are the most fundamental, mathematically, non-primitive cells are often chosen for convenience because they better reflect the higher symmetry of the overall lattice. It just makes the crystallographic analysis simpler sometimes.
So if we connect this to the bigger picture, the choice of unit cell isn't always straightforward.
Not always obvious, no.
While infinite basic units could mathematically generate the same lattice, we often choose cells that best reflect the object's overall symmetry, even if it means including more than one motif.
Right. It's like finding the most elegant way to describe the repeating pattern.
It makes sense.
Exactly. Even though many different geometric unit cells could technically describe the same crystal lattice, crystallographers have conventions to choose the one that most appropriately highlights the inherent symmetry elements.
And this principle carries over.
This principle of finding the most symmetrical representation extends to the next fundamental level of organization. The Bravais lattices.
Ah, the Bravais lattices. This sounds very foundational, almost like the universal building blocks for how repeating units can arrange themselves.
They are indeed. The Bravais lattices are perhaps one of the most fundamental classifications in crystallography.
What are they exactly?
They are the 14 distinct types of translational lattices that are compatible with crystal classes in 3 dimensions.
Only 14. That seems low.
It does, but it's mathematically proven. Think of them as the 14 fundamental blueprints for how points representing your motifs or unit cells can be arranged in a perfectly ordered, repeating fashion in space.
Just the arrangement of points, not the symmetry of the motif itself yet.
Exactly. They describe the translational symmetry only how the pattern shifts. To give you a feel for their significance, imagine trying to fill space with repeating units in every possible way while maintaining perfect periodicity.
Okay.
It turns out there are only 14 unique ways to do this based on the symmetry constraints.
Like simple cubic.
Yes, the simple cubic lattice is one where points are just at the corners of a cube. Then you have body-centered cubic, face-centered cubic.
More complex ones too.
And more complex monoclinic or triclinic lattices where the angles and side lengths are all different. These 14 fundamental arrangements are exhaustive. Any crystal's translational periodicity must be described by one of these 14 lattices.
So these lattices are like the ultimate foundational blueprints for how the repeating units of a crystal can be arranged in space.
The skeleton, if you will.
They dictate the skeleton upon which all the other symmetry operations are built. That's a powerful constraint on the physical world.
It really is.
Now we're diving into the really specific, rigorous mathematical rules that govern crystal structures.
Getting into the weeds now.
Because while symmetry is everywhere, crystals, by their very nature of being perfectly periodic, have to follow a very strict set of rules. And this leads us to something incredibly profound called the crystallographic restriction theorem.
This theorem is truly one of the cornerstone insights in crystallography. It answers a very specific yet incredibly profound question about crystal symmetry.
A question that might seem counterintuitive.
Yes, especially given the beauty of nature.
And the big question is, why can rotation axes in crystals only be twofold, that's 180 degrees, threefold, 120, fourfold, 90, or sixfold, 60?
The allowed rotations.
Why not fivefold or sevenfold symmetry, for instance? You see plenty of fivefold symmetry in nature, right? Like the petals of many flowers or the arms of a starfish.
You do. It seems common.
So why is it forbidden in crystals? What gives?
And this raises a truly important question. What exactly prevents other rotational symmetries in crystals?
It must be the periodicity.
The answer lies in the very definition of a crystal. Its perfectly periodic, repeating structure. The proof for this, often called the tiling argument, is remarkably elegant.
Okay, the tiling argument, how does it work?
Imagine a plane perpendicular to a given rotation axis. This plane intersects one of the unit cell vertices, right?
Got it. A point on the grid.
Now, if you apply an n-fold rotation around that axis, this vertex will create a regularly n-edged polygon as it rotates.
Okay, spinning the point creates a shape.
The critical constraint is that the vertices of this polygon must also be unit cell vertices. They have to land on other points in the periodic grid.
That's the restriction.
Exactly. For these polygons to perfectly tile the plane completely, meaning no gaps, no overlaps, covering the entire space without interruption.
Like tiling a floor perfectly.
Precisely. The geometry simply restricts n to 2, 3, 4, or 6. If you tried to tile a flat surface with regular pentagons, for example,
You'd get gaps. I've seen that.
you'd immediately see gaps or overlaps. The angles just don't fit perfectly together to form a continuous repeating pattern. The math shows their internal angles must add up to 360 degrees where they meet, and that only works for n equal 2, 3, 4, or 6.
So it's a fundamental consequence of needing to perfectly pile three-dimensional space with repeating units. That's why five-fold, seven-fold, or any other rotations are impossible for periodic crystals.
Impossible.
That is a truly surprising and elegant mathematical constraint on the very architecture of matter. It means the universe itself has a preferred geometry for its repeating structures.
It's an absolutely beautiful mathematical proof that underpins the entire field. It sets the fundamental boundaries for what a crystal can be.
And from this restriction.
From this restriction, we derive the crystallographic point groups, also known as crystal classes.
Okay, point groups or crystal classes. What exactly are these and how do they relate to what we've just discussed?
A crystallographic point group is the set of all symmetry operations, rotations, reflections, inversions, that pass through a single fixed point of a finite object, like an isolated crystal.
So the symmetry at a point, not considering the repetition yet.
Exactly. They essentially define the total macroscopic symmetry of that object, how it appears from the outside.
Okay.
Because these point groups must be entirely consistent with crystalline periodicity, meaning they have to obey the crystallographic restriction theorem we just discussed.
Only certain combinations are allowed.
Only 32 distinct point groups are allowed in the crystalline state of matter. These are the 32 crystal classes. Each class represents a unique combination of those allowed point symmetries. Rotations 2, 3, 4, 6, reflections, inversions.
32. That's it. Out of infinite possibilities.
Just 32 are compatible with repeating patterns.
So to connect this to the bigger picture, these point groups are powerful abstractions, right? Mathematical groups that precisely define the symmetry of the basic unit.
And thus the overall macroscopic symmetry of the crystal itself.
It's astounding that out of an infinite number of possible symmetries, only these 32 are permitted in the crystalline world.
It is. And as a subset of these, we have the low groups.
Low groups, what defines them?
Of the 32 crystal classes, only 11 contain the operator center of symmetry, that inversion center we discussed earlier.
The ones with inversion symmetry.
Yes. These 11 centrosymmetric crystal classes are known as low groups. They are particularly important in X-ray diffraction because the diffraction pattern itself often inherently shows this center of symmetry, which can simplify the interpretation.
Okay, makes sense. But wait, there's even more complexity.
Always more layers.
When you combine these point symmetries, which act around a single point, with the translational periodicity inherent in a crystal,
Bringing the translation back in.
you get even more sophisticated and fascinating symmetry elements. This is where screw axes and glide planes come in, which really describe the internal atomic arrangement.
Indeed. These are composite symmetry operations that include a crucial translational component. They involve both a symmetry operation and a movement.
Okay, so a screw axis, like a literal screw.
Pretty much. A screw axis, also called a helicoidal axis, involves a rotation followed by a translation along the axis itself.
So rotate and shift along the rotation line.
Exactly. For example, a 6/2 screw axis means a 60-degree rotation, 3606, combined with a translation of 26 of the unit cell axis length along that direction.
Like climbing a spiral staircase.
Perfect analogy. As you rotate around the central pole, you also move up or down. If you apply a two-fold screw axis to a left hand,
Yeah,
It rotates 180 degrees and moves, but it always remains a left hand, just shifted in space. These are very common in biological molecules like proteins and DNA, forming those helical structures.
Fascinating. And a glide plane, what's happening there?
A glide plane is a reflection followed by a translation parallel to the plane.
Reflect and slide.
Reflect and slide, exactly. So if a left hand were to encounter a glide plane, it would first reflect, generating a right hand.
Chirality changes.
Chirality changes, yes. And then it moves by half the lattice translation in the direction of the glide operation.
So these elements mix point symmetry and translation.
They do. They are absolutely crucial for fully describing the internal atomic level symmetry of crystals, accounting for how motifs are actually packed and repeated throughout the lattice in intricate, precise ways. They explain the difference between a simple mirror reflection and one that also involves a shift.
And when you put all these pieces together, the 32 crystal classes, point symmetries, with the 14 brevet lattices, translational symmetries, plus these screw and glide elements,
The whole shebang.
you arrive at something called space groups. This sounds like the ultimate comprehensive classification.
The space groups truly represent the ultimate and most comprehensive classification of crystal symmetry. They are the exhaustive combination of the 32 crystallographic point groups and the 14 brevet lattices, incorporating the translational symmetries of screw axes and glide planes.
And how many are there?
This yields precisely 230 different ways to replicate a finite object or motif in three-dimensional space while maintaining periodicity.
230, that's the magic number.
That's the magic number. These 230 space groups provide a complete mathematical description of every possible internal arrangement of atoms in a crystal. Every single conceivable periodic crystal structure fits into one of these 230 groups.
Wow. Okay, so if you see a space group symbol, like I saw CMM2 mentioned, there's like a secret code, what does that actually mean for the structure of a real material?
That's a fantastic question because the symbols are incredibly informative once you know the language.
Let's decode CMM2.
Okay. The C indicates that the brevet lattice is centered on the C-axis faces, meaning there are motifs not just at the corners of the unit cell, but also in the centers of the faces perpendicular to the C-axis.
Okay, C for C face centered.
Right. The first M signifies a mirror plane perpendicular to the A-axis.
One for mirror.
The second M represents another mirror plane, this time perpendicular to the B-axis.
Another mirror, different direction.
And the two refers to a twofold rotation axis parallel to the C-axis.
Got it.
So from just those four characters, CMMM, you can instantly visualize the internal arrangement and symmetry elements of that specific crystal. It provides a concise and comprehensive description of the crystal's full symmetry, telling a materials scientist exactly how atoms are arranged.
That's incredibly efficient. And finally, all these classifications, the 32 crystal classes, the 14 brevet lattices, and the 230 space groups can be elegantly grouped into just 7 crystal systems.
The top level of the hierarchy.
This seems like a higher-level organizational principle.
It is. These 7 crystal systems, triclinic, monoclinic, orthorhombic, tetragonal, trigonal, hexagonal, and cubic, are based on their minimum required symmetry and the fundamental geometry of their unit cells.
So group by shape and minimum symmetry.
Pretty much. Each system has specific metric restrictions, meaning requirements for the lengths of the unit cell edges, A, B, C, and the angles between them, alpha, beta, gamma.
Like cubic needs equal sides and 90-degree angles.
Exactly. A cubic system, the highest symmetry, has A, B, C, and all angles equal to 90 degrees. Think table salt or diamonds.
And the others are less restrictive.
Right. A monoclinic system, for example, has unequal edge lengths, ABEC, and 2 90-degree angles, but 1 non-90-degree angle. This allows for more complex, often elongated or flattened crystal habits seen in minerals like gypsum.
So what does this all mean, this huge classification system?
This hierarchical classification from the 7 systems down to the 230 space groups provides a complete and exhaustive mathematical framework to describe every single possible periodic crystal structure that can exist in our universe.
That's mind-boggling.
It's a testament to how profoundly ordered the natural world can be at its most fundamental atomic level.
The quest to understand crystals isn't a new phenomenon, is it?
Oh, far from it.
It's a story that intertwines ancient philosophy, groundbreaking scientific discoveries, and even, the harmony of the cosmos itself. It's a testament to humanity's enduring fascination with order.
Indeed. Humans have been captivated by the regular geometry and striking symmetry of crystals for millennia. They were often seen as expressions of perfect, everlasting beauty.
Almost mystical.
Almost mystical in their formation, yes. This fascination wasn't just aesthetic. It was an early attempt to decipher the hidden rules of the natural world.
We can trace this fascination back to some of the earliest thinkers. Theophrastus, way back between 371 and 287 BC.
Aristotle's successor.
He wrote On Stones, which is considered one of the first known systematic treatises on minerals.
Laying groundwork.
Later, Pliny the Elder in the 1st century AD, through his monumental Naturalis Historia, compiled vast amounts of observation.
A huge encyclopedia.
Providing the basis for mineralogical knowledge well into the Middle Ages. These were the encyclopedists of their time.
And it wasn't just observation and classification. Philosophers and mathematicians like Plato and Euclid were deeply interested in perfect forms.
The Platonic solids.
Exactly. They rigorously classified the 5 Platonic solids: the tetrahedron, the hexahedron, which is a cube, the octahedron, dodecahedron, and icosahedron.
These perfect shapes.
With their congruent faces, edges, and vertices, they captivated early thinkers as expressions of divine order or fundamental building blocks.
It's important to make a crucial distinction here, though, for our deep dive audience.
Yes.
While these shapes are geometrically beautiful, and some, like the cube or octahedron, can be observed in crystal forms, like fluorite or pyrite.
Common crystal shapes.
The dodecahedron and icosahedron cannot be crystal shapes in the traditional periodic sense.
That's right, and it loops back to our crystallographic restriction theorem.
The fivefold symmetry problem again.
Exactly. For reasons of translational symmetry, a perfectly periodic crystal cannot exhibit fivefold symmetry, which both the dodecahedron and icosahedron possess. So, while beautiful and abstractly perfect, they don't fit the strict rules of periodic crystalline order.
A profound realization connecting abstract geometry to the physical constraints of matter.
Definitely.
Moving forward to the Renaissance, a truly beautiful observation that many of us can appreciate today was made by Johannes Kepler in 1611.
Kepler of planetary motion fame.
The very same. His groundbreaking study of the unique hexagonal six-fold symmetry of snowflakes.
Ah, the snowflake pamphlet.
He published a small treatise, Strenasio de Nivis Sexangula, essentially a Christmas gift on the six-cornered snowflake.
Kepler wasn't just observing, he was actively trying to understand the underlying natural forces leading to these strikingly symmetrical structures.
You thought about packing too, right?
His work even included an early attempt to describe close packing, trying to determine the maximum density of sphere arrangements, a problem known as the Kepler conjecture.
Which took forever to prove.
Which, remarkably, wasn't fully proven until nearly 400 years later by mathematician Thomas Hales. This shows the long shadow cast by these early questions about natural order.
But the real scientific foundations of crystallography, moving from philosophical observation to systematic measurement, started forming in the 17th century.
Yes, that's when Nicholas Steno came along in 1669. He made a pivotal discovery.
Stena's law.
Articulating the law of constancy of interfacial angle. This law states that the angles between identical faces of a crystal are always the same for a given substance,
Regardless of size or shape.
regardless of the crystal's overall size, shape, or specific growth conditions. Imagine measuring the angle between two faces of a quartz crystal. It will always be the same, whether the crystal is tiny or enormous.
That's huge. It implies internal consistency.
It marked the true beginning of crystallography as a quantitative science.
And it was empirically proven later, confirming Steno's careful observations.
Exactly. Jean-Baptiste Romé de Lisle, in 1783, through painstaking work, systematically examined about 500 different crystals,
500.
providing robust empirical proof for Steno's law. He categorized and measured, building a massive data set.
Then came Hauy.
Then, at the turn of the 19th century, René Just Hauy came along. He's widely and rightly called the father of crystallography for a reason.
What did Hauy do that earned him such a title? Was it a single brilliant insight?
It was a monumental conceptual leap. Hauy famously observed how a broken calcite crystal always fractured along specific flat planes,
Cleavage planes.
producing smaller pieces with the same fundamental angles. From this, he proposed a revolutionary idea. Crystals consist of smaller, repeating, integrating molecules,
Like tiny building blocks.
what we would now call unit cells or motifs that possess the same fundamental structure and symmetry as the crystal itself.
That explains Steno's law.
This fundamental finding elegantly explained Steno's law, demonstrating why those interfacial angles were constant. It laid the complete theoretical groundwork for our modern understanding of crystal structures as periodic arrangements of basic repeating units. He essentially gave us the conceptual framework for the unit cell.
But the truly modern revolution, the ability to see this hidden atomic architecture and confirm Hoy's hypothesis,
That came later.
came in the early 20th century with the advent of X-ray diffraction. This must have been a game changer.
It was an absolute paradigm shift. Before this, crystallography was largely about external morphology and mathematical deduction.
Looking from the outside.
Then, in 1912, Max von Laue made his groundbreaking discovery. He showed that crystals diffract X-rays.
They bend the X-rays?
They scatter them in very specific directions, producing highly regular, crystal-dependent patterns of points on a photographic plate.
Direct evidence of internal order.
This was direct evidence of the internal periodic atomic structure. He won the Nobel Prize in Physics in 1914 for this.
And then, almost immediately, the Bragg father and son duo, William Henry and William Lawrence Bragg,
Built on Laue's discovery.
built on this foundational discovery to unlock even more.
Indeed. In 1913, just a year after Laue's discovery, they developed Bragg's law,
Which let them map structures.
showing how X-rays could be used to precisely define the atomic positions within a crystal lattice, essentially allowing scientists to map out its full three-dimensional structure.
Another Nobel Prize.
They, too, won the Nobel Prize in Physics in 1915 for their pioneering work. Their contributions transformed crystallography from a geometrical discipline into a powerful, direct method for determining atomic and molecular structures.
Giving us an unprecedented view into the heart of matter.
Exactly.
The impact of X-ray crystallography has been monumental, extending far beyond just minerals.
Oh, absolutely. Biology, chemistry.
It allowed for the determination of the structures of incredibly complex molecules like cholesterol, penicillin, insulin,
Things vital to life and medicine.
and of course the groundbreaking discovery of the iconic DNA structure by Watson, Crick, and Wilkins.
Which earned them the Nobel Prize in 1962.
Relied heavily on X-ray diffraction data, particularly Rosalind Franklin's seminal work.
Her crucial Photo 51.
It quite literally unveiled the blueprint of life itself, all thanks to understanding how X-rays interact with a crystalline, ordered arrangement of atoms.
A truly transformative technique.
Just when scientists thought they had all the rules of crystal structure figured out based on centuries of observation and the powerful insights of X-ray diffraction,
Uh-oh.
something completely unexpected came along that completely rocked the world of crystallography. Get ready for a truly surprising fact.
Indeed, it challenged a fundamental tenet that had stood for centuries, something we just discussed as an absolute truth.
That crystallographic restriction.
The crystallographic restriction theorem, yes, which prohibited certain rotational symmetries in periodic crystals.
So what exactly happened? What was this revolutionary discovery that broke the rules?
In 1982, an Israeli material scientist named Dan Shechtman discovered something truly astonishing.
What was he looking at?
He was studying what he found was that this material produced clear, distinct, point-shaped diffraction patterns, just like traditional crystals.
Indicating order.
This unequivocally indicated an ordered internal structure, not an amorphous, disordered one.
But I'm guessing there was a catch, and a big one, given what we know about the crystallographic restriction.
There was a massive catch, one that initially led to significant skepticism and even ridicule from some senior scientists in the field.
Ridicule. Really?
Oh, yes, because these diffraction patterns showed unmistakable five-fold symmetry.
The forbidden symmetry.
The forbidden symmetry. As we painstakingly explained earlier, the crystallographic restriction theorem had mathematically proven that five-fold symmetry is impossible for periodic crystals. It simply cannot tile three-dimensional space without gaps or overlaps.
This raised an important question, a scientific paradox.
A huge one.
If these materials had sharp diffraction patterns, which indicates order, but displayed an impossible symmetry, what were they?
What do you even call them?
They certainly weren't crystals in the traditional sense, which by definition rely on strict periodicity. It's like finding a square peg that somehow perfectly fits into a round hole, but the peg insisted it was round.
Right. It challenged the very definition of a crystal.
It must have caused a stir.
Exactly. This unexpected and seemingly impossible phenomenon led to the naming of a completely new class of materials, quasicrystals.
Quasicrystals, okay.
They display clear diffraction points like traditional crystals, but crucially, They do not possess periodic translational symmetry,
No repeating grid.
no strictly repeating grid. This means they can exhibit rotational symmetries other than the allowed 2, 3, 4, and 6-fold orders,
Like fivefold.
such as 5-fold, 7-fold, 8-fold, or even higher, which were previously thought to be forbidden in ordered matter.
So how do they manage this impossible trick of having order and sharp diffraction patterns, but without strict periodicity? What's the underlying structural secret?
They do it through what's called quasi-periodic tiling.
Quasi-periodic, meaning almost periodic.
Sort of. British mathematician Roger Penrose had already explored such non-repeating yet ordered patterns in the 1970s, now famously known as Penrose tilings.
Penrose tiles, I've seen pictures with the kites and darts.
Exactly. Those tilings don't repeat periodically in the way a chessboard does, but they still have a precise, deterministic, and ordered structure.
How so?
Any finite patch from a Penrose tiling can occur infinitely often, but it never strictly repeats in a periodic fashion. Sheckman's quasicrystal alloys exhibited these very quasi-periodic patterns, often showing a local 5-fold symmetry in their atomic arrangements.
So order without perfect repetition.
It's an order without periodicity, a subtle but profound distinction.
That's incredible. And it turns out similar quasi-periodic patterns had actually been found much earlier, centuries before Penrose or Sheckman, hadn't they?
That's another surprising historical tidbit.
Where?
Yes, surprisingly, similar quasi-periodic patterns demonstrating what we now recognize as 5-fold symmetry were discovered and intricately crafted in elaborate Islamic ornaments from the Middle Ages.
Wow, they knew.
Well, they had intuitively grasped these complex, non-repeating patterns long before mathematicians or crystallographers formally described them. Amazing craftsmanship and geometric intuition.
So Sheckman's discovery, it wasn't controversial.
Hugely.
Oh.
The discovery of quasicrystals by Sheckman, for which he eventually received the Nobel Prize in Chemistry in 2011 after years of controversy and resistance,
Vindicated.
quite literally necessitated a revised definition for traditional crystals. The new definition no longer solely relied on sharp diffraction patterns, but explicitly included translational symmetry as an independent, required property for a substance to be called a crystal.
So quasicrystals are no longer seen as rule breakers, but have their own distinct, albeit expanded, set of rules within an expanded understanding of material structures.
Exactly. They've forced us to broaden our very definition of crystal.
They've carved out their own space.
Precisely. And they aren't just a scientific curiosity. They have very real practical applications.
Like what?
Quasicrystals are increasingly important for technical applications due to their special and often unique material properties. Things like high hardness, low friction,
Non-stick surfaces.
non-stick surfaces, excellent thermal insulation. They're opening up entirely new avenues in materials science and engineering.
So from ancient observations of perfect forms to groundbreaking modern discoveries that redefine our understanding of matter.
It's been quite a journey.
Symmetry has been a constant guiding thread in humanity's quest to understand the world. But how is this fundamental understanding being used today, especially with cutting-edge technology like artificial intelligence?
The modern age.
Are computers starting to see and understand symmetry in the way we do?
It's an incredibly exciting time because our deep fundamental understanding of crystallographic symmetry is not just academic, it's proving absolutely pivotal in designing and discovering the advanced materials of tomorrow.
We're moving from observation to engineering.
To precise predictive engineering, yes.
It sounds like understanding symmetry is crucial for comprehending and manipulating materials at the atomic and molecular levels. Can you elaborate on why that connection is so strong?
Absolutely. The repetitive, ordered arrangement of atoms within a crystal lattice, precisely guided by those symmetry operations we've been discussing,
The space groups, the unit cells.
fundamentally dictates a material's distinctive macroscopic properties. For instance, materials with high degrees of symmetry often exhibit unique optical, electrical, and magnetic characteristics.
Symmetry equals special properties.
Often, yes. This knowledge isn't just theoretical, it's vital for developing advanced materials for everything. Faster electronics, more efficient solar cells, targeted drug delivery systems, ultra-sensitive sensors, highly selective catalysts.
The list goes on.
By understanding the symmetry, we can predict and then intentionally design materials to have tailored properties for specific applications.
And how are scientists actually observing and analyzing these symmetries at such tiny atomic scales today? It must have evolved significantly from the early X-ray diffraction techniques.
It has advanced tremendously. Recent technological breakthroughs have truly enhanced our capabilities, allowing us to peek into the atomic realm with unprecedented clarity.
Like better microscopes.
High-resolution imaging techniques such as transmission electron microscopy, or TEM, and atomic force microscopy, AFM, allow researchers to directly observe crystal structures and their symmetry elements.
Seeing individual atoms?
Even individual atoms and their arrangements at the nanoscale. Additionally, advanced X-ray and neutron diffraction methods continue to be refined.
Still important.
Ah, yes. Facilitating even more accurate and detailed determination of crystallographic symmetry in increasingly complex and novel materials. We're directly visualizing the consequences of these symmetry operations.
Beyond just observing, are we also predicting material behavior based on symmetry even before we synthesize them in the lab? That sounds like a powerful leap.
We are, and this is where computational power becomes indispensable, through sophisticated computational approaches like molecular dynamics simulation
Running simulations.
and density functional theory, or DFT, calculations. Researchers are able to predict and understand how materials will behave based on their exact crystallographic symmetry.
Designing on computers first.
These methods are critical for the in silico design of novel materials with precisely tailored properties. Instead of endless trial and error in the lab, we can now simulate and optimize structures digitally, guided by symmetry principles.
And this brings us to the very forefront of research. Machine learning, ML models, and symmetry perception.
The AI angle.
I understand there's been a particular challenge here for traditional AI models when it comes to seeing the full range of crystal symmetries.
What's truly fascinating here is how we're now teaching computers to not just process data, but to actually see and understand these profound symmetries in a way that aligns with physical laws.
Teaching AI physics.
In a sense, yes. Machine learning is opening unprecedented avenues in materials design. The core challenge for many existing ML algorithms, particularly conventional convolutional neural networks.
Which are good at images.
Right. While they are excellent at preserving translational symmetry, recognizing a pattern no matter where it appears, they often struggle to intrinsically encode the full range of crystal symmetries.
The rotations, reflections.
We're talking about operations like rotation, inversion, reflection, and the more complex screw rotation and glide mirror operations. They essentially forget or fail to properly process these symmetries during their learning process.
So if these traditional models aren't seeing all the symmetry that's inherent in a crystal, their predictions for material properties might not be as accurate.
Exactly, or as physically consistent as they could be. This lack of full, explicit symmetry perception can lead to less accurate property predictions, especially when dealing with complex crystal structures where these symmetries play a crucial role.
So we need smarter AI.
That's why a revolutionary new ML model called the Symmetry Enhanced Equivariance Network, or SEN model, was recently developed. It directly addresses this fundamental limitation.
SEN model. How does the SEN model work to overcome these limitations and genuinely perceive crystal symmetries? It sounds like a significant breakthrough.
The SEN model is ingeniously designed. It identifies structure equivalences and accurately predicts material properties by building a material representation that explicitly incorporates joint structure chemical patterns and their symmetries.
How does it do that?
First, it learns detailed chemical environments for each atom, considering its type, connectivity to neighbors, bond lengths, angles, etc.
Local environment.
Then it uses a specialized component called a capsule transformer, which is specifically engineered to perceive and inherit diverse crystal symmetries. Scaling, translation, rotation, reflection, inversion reflection, mirroring reflection, all of them.
Wow. Built-in symmetry awareness.
This ensures equivariance, a crucial property.
Equivariance.
Meaning that if you apply a symmetry operation to the input material, the model's output changes in a predictable corresponding way. In essence, equivalent patterns contribute identically to property predictions.
Which is how physics works.
Which is exactly how physics tells us properties should behave.
That sounds incredibly powerful,
Yeah.
effectively building the laws of physics directly into the AI. What kind of results are they seeing with this advanced approach?
The SEN model has shown remarkable precision and efficiency. For instance, when predicting crucial material properties like band gap,
Which affects conductivity.
exactly, it achieved a mean absolute error of just 0.181 eV, which is tiny. For formation energy, how stable a material is.
Right.
Its error was an astonishingly low 0.0161 eV per atom.
That's incredibly accurate.
These results significantly outperform older, less symmetry-aware models, and they do it by effectively reducing effective feature dimensionality through the superior symmetry perception.
Meaning it's more efficient because it understands the symmetry.
Exactly. By correctly understanding the symmetry, the model needs less data and makes more robust predictions, especially in crystal systems with higher degrees of symmetry. This leap forward is accelerating the design of novel materials with unparalleled accuracy.
Harnessing the universe's hidden order with digital tools.
You got it.
And that wraps up our deep dive into crystallographic symmetry. We've journeyed from the everyday beauty of a perfect snowflake through the intricate mathematical rules governing crystal formation,
The 32 classes, 230 space groups,
to the revolutionary discovery of quasic crystals that forced us to rethink our very definitions, and now to the cutting edge of AI-driven materials science.
it's quite a story.
It's a profound testament to the fact that the more closely we examine our world, the more intricate and beautiful the underlying order we discover.
It truly is. This journey reveals the universe's inherent design principles, from the largest galaxies to the smallest atomic structures. The profound beauty of this hidden order is truly everywhere,
If you know where to look.
patiently waiting to be seen and understood by those who look closely enough.
So what does this all mean for you? It means that understanding symmetry isn't just an academic exercise confined to laboratories or textbooks.
Not at all.
It's a key to unlocking the universe's fundamental design principles. Whether those principles are shaping the vast structures of the cosmos or the tiniest arrangements of atoms. The elegance and profound implications of this hidden order are truly everywhere once you know how to look.
This raises an important question. Now that you've journeyed with us and learned about these profound symmetries and the hidden mathematical order that governs the material world,
Yeah.
what new wonders will you discover by simply looking for the hidden order in the world around you?
Just by observing more closely.
From the mundane patterns on a sidewalk to the magnificent geometry of a gemstone, the universe is constantly displaying its structural secrets.
Take a moment to appreciate the perfect angles of a common salt crystal, the repeating patterns in a paper fabric, or even the subtle way your own hands mirror each other.
Keep exploring.
Keep questioning and keep diving deep into knowledge. We'll see you on the next deep dive.